So we have a graph and we want to find the shortest path from some node to all other nodes. If this was a weighted graph, then we could use Dijkstra's algorithm to solve this problem. And if it was an unweighted graph, then we could use the breadth first search algorithm. It's worth pointing out that an unweighted graph is really a weighted graph where all the weights are 1. So we could also use Dijkstra to solve it if we wanted to. Or a more intuitive way to think about the unweighted graph is that we are counting the number of steps needed to reach a node. Most people find breadth first search easier to understand and easier to implement than Dijkstra's. So the point of this video is to show you how you can actually transform a breadth first search into the Dijkstra's algorithm with one simple change. I'm going to start off talking about naive solutions, then we will move on to breadth first search and eventually Dijkstra's. So if you are already familiar with this problem, you may wish to skip some parts using the navigation links in the video description below. So the most obvious way to solve this problem is that we just try all possible paths and choose the shortest one. Let's say we wanted to get from A to E. One possible path would be from A to C to D and then back and forth several times between D and C and eventually from D to E. Since we can go back and forth as many times as we like, there is an infinite number of possible paths and we can just try them all. And you can imagine you might also have a longer cycle that would go like this. It doesn't apply to our graph right now, but you can imagine you might have a longer cycle and the same problem there. But since we are only interested in the shortest path, we don't really want to try those paths anyway, since any path which visits a node more than once is going to be longer than some other path which visits a node only once. So let's define a reasonable path as one which visits each node at most one time. If we tried all reasonable paths within this graph, then we would find the shortest path very quickly. But you can imagine if we had a larger graph, then the number of possible reasonable paths would still be so high that you might not have time to just try them all. And next we're going to see how breadth first search solves this problem faster. The idea is that we first visit all nodes at distance 1. So we've designated A as our start node, and we know we can get to C and D with one step from A. So we visit both C and D, and as we visit these nodes, we also learn which nodes are at distance 2, which in our example would be E and B. So we will visit all nodes at distance 1, and then we will visit all nodes at distance 2. And you can imagine if the graph was larger, then it would go on the same way until you eventually have discovered the shortest path to all nodes. And the way we're going to implement this in practice is with a regular queue. First in, first out, similar to how a queue at a grocery store might work. And we're going to follow this pseudocode. I'm not going to explain how it works because I think it's easier to learn by example. So we're going to solve this graph here using this queue and this loop. Before we enter the loop, we're going to put one object into the queue. The A represents that we are at node A, and the 0 represents that we have traveled 0 steps so far. Now we enter the loop. We will pull the first item from the queue. Have we visited A before? We haven't. If we would have, then we would do nothing and we would just pull the next item. But we haven't, so now we will visit A. We will mark it as visited. and we will add its neighbors to the back of the queue. Now we can get to D with one step from A, and we can get to C with one step from A. Now the order in which I added these is arbitrary. We would get the same result if I added them in the other way. It doesn't matter. Now we are done with A, and we will pull the first item from the queue. Have we visited D before? We haven't, so we will visit it now and mark it as visited. And we will add its neighbors. The 2 comes from the one step which we have already traveled and the one step it takes to get from D to C. And then we will also add a similar object for E. And now we are done. So we will pull the first item from the queue. Notice that we have 2 objects in the queue representing the same item, the same node, sorry. This is not going to be a problem because we're only going to visit each node once. So the second time we come across it, we're just not going to do anything. And a property of breadth first search is that the first time you get to a node is always going to be the shortest path to that node, which in the case of C is right now. We haven't visited C before, so we are visiting it now. We will mark it as visited, and we are learning that the shortest path to C is one step. So we would write this down somewhere if we wanted to save that information. And then we will add C's neighbors. So we will add D2, and we always add to the back of the queue. And we will add B2. Now we are done with C, so we will pull the first item from the queue. Have we visited C before? Well, yes, we just did, so we will do nothing. We will just pull the first item from the queue. And have we visited E before? We haven't, so we are visiting E now. We are learning that the shortest path from node A to node E is 2 steps. We could write this down now. And also, if we wanted to learn the actual path ADE, we could do that by also saving inside these objects the information of the node from which we arrived. So, for example, we could have an object that looks like this. So this would mean that we are now at node E, and we came there from node D, and the total distance that we have traveled has been 2 steps. And as we visit this node, we could write this information down somewhere, and then we would have the complete history of the path using the information we gain at each node. But for this video, we're just going to look at the total length, the length of the shortest path. We're not going to actually care about the actual path that we take. So anyway, we will add E's neighbors, or in this case neighbor, B3. So the 2 steps that we have already traveled plus this 1 step here. And now we are done with E, and we will pull the first item from the queue. Have we visited D before? Well, yes, we have, so we will do nothing. Just pull the next item from the queue. Have we visited B before? We have not, so we will visit it, mark it as visited, and we also learned that the shortest path to B is 2 steps. And B doesn't have any outgoing arrows, so we're not going to add any neighbors this time, but we would if it had any. And then we will pull the last item from the queue, which is also for B. Have we visited B before? Yes, we have. so we will do nothing. And our queue is empty, so we are done. We have learned the shortest path from node A to all other nodes. Now think about what would happen if you tried to do the same thing on a graph with weighted edges. So if you try to use breadth first algorithm to solve the shortest path from node A, what would happen? In particular, what would go wrong? That's awkward. Let's see. Nope. There we go. Sorry about this. All right. So we can see that the shortest path has now changed. So well, some of the shortest paths have changed. If we wanted to get from A to E, then the shortest path used to be ADE, but now that has a cost of, or a distance of 25, and the shortest path now goes from A, C, D, E for a total distance of 18. And it's not gonna work, but we're gonna try anyways. So we're gonna try to solve this using breadth first search, and we're gonna try to figure out what goes wrong and how can we fix it. So as usual, we're going to start off by adding one object into the queue, representing that we are starting from A with 0 distance traveled so far. Then we enter the loop. We will poll the first object. Have we visited it before? No. So we will visit it now, and we will add its neighbors to the queue. So we can get to node D with 10 cost or 10 distance, and we can get to node C, which is at distance 2. Now we are done with A, and we will pull the first item from the queue. Now you may notice that our idea was to visit all nodes at distance 2 before we visit any nodes at distance 10. But you can see what is happening right now is that we are about to visit node D, which is at distance 10 from A, despite the fact that we still haven't visited node C, which is at distance 2 from A. So we are breaking our idea right here, but let's see what happens. So have we visited D before? No. So we will mark it as visited, and then we will add its neighbors. So we will add, let's see, we will add 11 distance to C, and we will add 25 distance to E. And as we are visiting node D, we are also learning incorrectly that the shortest path from A to D is 10 distance. Now you might be thinking that, hey, we might learn the 3 distance route later. But if you remember how our algorithm works, we always check, have we visited this node before? And since we have visited D before, we're not going to actually learn this shorter route later. Now feel free to pause the video and think about how you might try to fix this problem. One way to fix it would be to check if the new route we found was better than the old one. In this case, the 3 is better than the 10 that we have discovered previously. So we would continue the search from there despite the fact that we have already visited D. This would work, but it would be very slow in many scenarios. We might end up searching all routes which visit each node at most one time, which is essentially a brute force solution, and as we talked in the beginning of the video, it would be too slow for many scenarios. What makes breadth first search and Dijkstra fast is the fact that we only visit each node once. Now let's go back a bit and go to the beginning of the search after we have processed node A. A better solution has something to do with the queue. If you're not sure what it is, feel free to pause the video again and think about it for a while. So our queue always gives us the object which was added first when we actually want the object which has the smallest distance. In the case of unweighted graphs, those two goals are the same. In the case of weighted graphs, those two goals are conflicting, as we just saw. Now we can use a priority queue where objects are sorted based on their distance property. Let's see how that would work out. So the priority queue sorts them based on their distance. So we would pull the first item from the queue, and this time it would be the C2 rather than the D10. Have we visited C before? We haven't, so we will mark it as visited, and then we will add its neighbors to the queue. So we can get to D with a total of 3 distance, and we can get to B with a distance of 32. Notice that I didn't add all of the objects to the back of the queue because, again, the priority queue keeps the objects in order. Then we will pull the next item from the queue. Have we visited D before? We haven't, so we will mark it as visited, and now we are correctly learning that the shortest path from A to D is at 3 distance. Then we will add its neighbors, so we will add C4. Where are you? Okay, it's like I don't have a C4, so there we go. We can go back to C with a distance of 4, and we can go to E with a distance of 18. Now we are done with D. So we will pull the first item from the queue. Have we visited C before? Yes, we have, so we will do nothing. We will pull the first item from the queue. Have we visited D? Yes, we have, so we will do nothing. Have we visited E? No, we haven't. So now we are learning that the shortest path to E is 18 distance, and we are marking E as visited, and we are adding its neighbor into the queue. So that's 26, I think. Okay. And notice again that the priority queue keeps them in order. So we will find that well, let's just do it. So we're done with E. We will pull the first item from the queue. And we haven't visited B before, so we will mark it as visited, and then we are learning that the shortest path is this 26 path right here and not the 32 path here. And we would add B's neighbors if it had any, but it doesn't, so we will just pull the first item from the queue. Have we visited it? Yes, so we'll do nothing, and our queue is empty, so we are done, and we have successfully learned all the shortest paths from node A. If you guessed it, this is the Dijkstra's algorithm, and it's not usually presented this way. If you look it up, it's usually explained with concepts like distance estimation and edge relaxation and all that kind of stuff. but I just find it much simpler to think of it as an extension of breadth first search, where we simply change the queue to a priority queue. I hope this video was useful to you. If you have any questions or if you spotted any mistakes, let me know in the comments.